Trigonometric identities. We're going to be solving identities. In other words, what we're going to do is we're going to transform one side to make it look like the other side. To prove, what we're doing is proving that that statement up there is true. That's the idea behind doing trigonometric identities, proving trig statements true. Okay. Now, guidelines for establishing identities. These are important. One, it is almost always preferable to start with the side containing the more complicated expression. So you generally want to work with the more complicated side and simplify it. It makes sense. It's a lot harder to take something simple and make it complex, although I've seen some of your attempts at solving problems. But generally speaking, it's much easier to take something complex and make it simple. Okay? Rewrite sums or differences of quotients as a single quotient. So if you have fractions that are being added and subtracted, make them one fraction. Get common denominators, make them one fraction. That's a very common step to do. Rewriting one side in terms of sine and cosine functions may help. One of the most common things that I do when I'm doing this is, okay, anything that's not sine or cosine on one side, I work with one side, I make them all sine or cosine. That is often one of the things that I will do straight up, right off the bat, is make everything sine and cosine. Get rid of tangents and cotangents and secants. Get rid of all that stuff. Make it all sines and cosines. It's generally much easier to work with. Not always. Okay. Always keep your goal in mind. As you manipulate one side of the expression, you must keep in mind the form of the expression on the other side. So we want to make one side look like the other side. Keep in mind what you're trying to make it look like. Okay, so like on that first one we're going to do, I want to get cosine theta. As I'm working on this side, what can I get rid of? What do I need to get rid of? What do I cancel? What do I reduce to get just cosine theta? That's my goal. I want to keep in mind as I'm working the problem. And the last part is the only absolute hard and fast rule when you're working trig identities. All the rest of them are just very strong suggestions. The only hard and fast rule is the last one. You cannot use such methods as adding, subtracting, multiplying, or dividing. This multiplying is missing from there. The same expression to each side. You do not solve this like an equation. Do not add 2 to both sides to solve for x. You don't do that here. You don't work both sides at the same time. You work one side at a time. You don't work both sides. You work one side at a time. Okay? Most of the ones you have working one side only is all you need to do. You can leave the other side alone. I have had ones, and sometimes when you get some really nasty ones, where you work one side and then you work the other side separately. You're not doing the same thing with both sides. Kind of like you meet in the middle. I've done that a couple of times. That's extremely rare, and that was some serious college level treatment I was doing. Don't think we're going to get anything that method, none of the examples that I've done would require that. Okay, so those are the rules. And like I said, the last one is the only hard and fast rule. The most of the rest of them are pretty much strong suggestions. Okay, strong suggestions. Don't be afraid to retry a problem if it's not working out. Don't be afraid to start over. If you do start over, don't erase everything you had, because you may have been headed in the right direction and just got stuck and didn't realize it. But when you start over, you go, oh, wait a minute. This is what I should have done over here. And then you can finish off where you started on the first side of the problem. But if you erased it all, it's gone. If you start over, don't erase what you've already done. Just start the problem again in a different space, start it over there. Does that make sense? And that's really a good rule. I know when I worked with calculus, when doing the for the AP testing, when you're doing the free response questions where you have to show your work, their rule is if you start a problem over, don't erase what you did. Just start the problem over. When you get done, cross out the part you did before. One, you want to save time by not erasing everything. Two, maybe you were going in the right direction the first time and your second time was all wrong, And you realize it's all wrong when you get there, and then you cross out your second attempt, not your first one that you erased. Okay? And then you're screwed because you got to go back. Oh, I did it right the first time. You erased everything, and you got to do it all over again instead of leaving it there until you're done. If you start one of these over again, don't erase what you did. Just start the problem over again in another space. And then go back to it if you need to go back to it, or cross it out when you're done saying, no, this isn't what I wanted. Okay, don't erase your work, because that may be where you may have been heading in the right direction, just got stuck. Okay? So we only have a few examples, and you'll see why we only have a few examples. All right, so I look at the first one here, 1 minus sine squared theta over 1 minus cosine theta equals negative cosine theta. I'm going to work with the more complicated side first, which means I'm going to work with the left-hand side. That's the one I'm going to rearrange. And what you're going to do is you're going to try to simplify it. I'm going to use these as best I can to do substitution. And you look at that and you go, okay, where can I start? There are some places to start. I look at that one and I see, okay, I see sine squared theta. I see sine squared theta, and my head goes to that right there. Goes to the Pythagorean identity. If I see cosine squared, or I see sine squared, or I see tangent or secant or cotangent or cosecant squared, that's kind of where my thought process leads to. I'm going, that's probably something to deal with here. Now, I don't have sine squared by itself here, but really just subtract cosine, you get sine squared theta equals 1 minus cosine squared theta. And you go, oh, if I do that, then I don't have any sines in there. All I have are cosines, and things will probably work out. I've taken it down. I want one trig function, cosine only. I want to get rid of the sine. I don't want to have any sines in there. I want cosines only. So my first thing is to take that sine squared theta, replace it with 1 minus cosine squared theta. So I have 1 minus cosine squared theta over 1 minus cosine theta equals. And the idea is I want to work it down so it gets to the other side. I'm only working one side at a time. I don't need to carry the other side. Okay, I don't need to keep carrying the other side down. And that'll actually be nice, saving a little room here. Okay, and I know some of you are going, okay, that didn't help. Well, the numerator, 1 minus cosine squared, is the difference of two squares. 1 squared minus cosine squared, which is factorable. Bless you. So I get 1 minus 1 plus cosine theta, 1 minus cosine theta, all over 1 minus cosine theta. Difference of two squared. A squared minus b squared is a plus b times a minus b, right? That's what I had there. Does that make sense? That one. Okay. What do I do next? This next one should be obvious, I hope. Cancel. Reduce. Yeah, I have a 1 minus cosine theta and a 1 minus cosine theta. They're gone. Which gives me 1 minus 1 plus cosine theta. But I want negative cosine theta. Let's, yeah, distribute the negative. 1 minus 1 minus cosine theta. And what happens? My 1 and minus 1 cancel. And I end up with 1 minus cosine theta. And that equals that. I'm done. That's what you do. Yeah, you just make one side look like the other side and you're done. That's the whole idea of proving an identity. You manipulate one side till it looks like the other side. using trig identities we know and have proven. Technically, we could use that one. If we have 1 minus sine squared theta over 1 minus cosine theta somewhere, we can now replace that with negative cosine theta. We could technically add that to our list of identities that we can use because we've proven it. It wouldn't be very helpful. I'm going to tell you it's not worth it. Okay, there are times when I've had to do that before, but here it's generally not really worth it. It's not something I'm going to add to my list because, frankly, you're not going to see that again unless it's a problem that I'm making you do. Okay. So, ready to look at number 2? Any more questions on number 1? Number 2. So, this is another one. It's not pretty. Okay. It looks like the side on the left, or sorry, so the side on the right looks more complicated, does it not? Because you got a fraction, and fractions are complicated. However, what are the trig functions that I have on that side? On the right-hand side, it's sine and cosine. Sine and cosine are as simplified as you can get with trig functions. They're the basic trig functions. If you have stuff in terms of sine and cosine, that's kind of where you want to head. It's much easier to do that. So what I would rather do on number 2, even though the fraction looks more complicated, and that's generally a good place to start. If you look on the left-hand side, I've got secant and tangent, and secant and tangent are actually more complicated because they're not in terms of sine and cosine. And one of the first things I almost always do, not always, but I almost always do, is if I don't have sine and cosine, I make sine and cosine. So my first step there is to get rid of the secant and the tangent and rewrite them in terms of sine and cosine. So the secant is 1 over the cosine of, I think that's delta, I don't really care. And then the tangent is sine over cosine. Well, that's not too bad, right? What do you think the next step should be? Just subtract them. They already have a common denominator, right? Combine them up into one fraction. So I have 1 minus sine of delta over the cosine of delta, and next time I'm going to change that variable. Okay. Oh. Okay. Anybody got any ideas? Yeah, 1 minus sine squared. Yeah. But we have 1 minus sine, not 1 minus sine squared. However, that is a step in the right direction. That is a step in the right direction. You're kind of thinking the right way. I can't take the square root. The square root of 1 minus cosine squared is not 1 minus cosine. Okay, when you have a subtraction, it's the square root of things subtract. It's not square root of the first minus square root of the second. You can't do that. However, I can make that numerator 1 minus sine squared. This is something I honestly don't think you guys would remember, and that's okay. Going back to our algebra 2 roots, when we had, and I think we did this in here too, but when you had like I in your denominator, and you had to get rid of it, you multiply by the conjugate, you can multiply by the conjugate to kind of do the same thing here. And like I said, it's not something I think you would think of, but if I multiply by 1 plus sine, over 1 plus sine. Because what am I actually multiplying by? I'm multiplying by 1. Right? When your numerator and denominator are the same, you're multiplying by 1. So I'm not changing the value. I'm just changing how it looks. So when I look at this, I have exactly the same thing except for plus and minus. It's the square of the first minus the square of the second. 1 minus sine squared over, and do not distribute. You'll understand why. Yeah, as long as I'm only doing it to one side, I can do whatever I want. I can do substitutions. Now, I didn't. What am I actually multiplying by here? 1. I'm multiplying by 1, right? This technically, what's the value of this? 1, right? This is 1. So can you multiply by 1? Yeah, if you multiply by 1, do you change its value? No, all I'm doing is changing what it looks like. I'm not changing its value here. Multiplying by 1 is okay. You can always multiply by 1. You can't, I couldn't multiply just the numerator. I have to do both. I have to do it like this, because this is 1. I can't just multiply just the numerator only. I have to multiply both the numerator and the denominator by the same thing. That I can do. I cannot just multiply by anything. But I can multiply by 1, which is technically what I'm doing here, right? This doesn't look like 1, but that's what I'm doing here. So my numerator is out, my denominator. Do not multiply it out and distribute it. And if you look at what I have, my denominator already contains what I want my denominator to contain. Right? My denominator contains whatever I want my denominator to contain. I need to get rid of the cosine in the denominator. Well, I have 1 minus sine squared, which is just like what I have here. 1 minus sine squared would be equal to cosine squared, because I can also rearrange this one. Remember, this one thing here, all 3 of those identities come from this one. Just rearrange. You can rearrange an identity that you have like this. You can rearrange this equation, that's fine. That's what I have here. So, I have 1 minus sine squared, replace it with cosine squared.
Wait, you said you can't change the value, but if you multiply it by 1,
I changed how it looked. I didn't change what it was worth.
Well, because you made it a square.
So, it still doesn't change how it's worth. What's this? This is 1. This fraction here is 1.
Yeah.
It doesn't look like 1, but it is 1, right? Because the something over itself is 1. 1 times anything is that anything. I'm just changing how it looks. I'm not changing its value. What's 2 times 1? It's 2. If I multiply 2 times 3 over 3, it's still 2. It just looks like 6 over 3. But it's still 2, right? That's what we're doing here. Okay? So remember when you were simplifying radicals and you had 3 over the square root of 2, what did you do? You multiplied by root 2 over root 2. Why could you do that? Because root 2 over root 2 is 1. You were changing what it looked like, not what it was worth. That's what I'm doing here. Does that make sense? Clear as crystal? Yeah. Clear as mud? Okay. So, do the substitution here. Cosine squared over cosine 1 plus sine. Cosine squared on top. And this is easy. I have cosine squared over cosine. What happens there? Yeah, my cosines cancel. One of my 2 cosines in the numerator cancels with my cosine in the denominator. And what do I have? I have cosine delta over 1 plus sine delta n. That's what we started with on the other side.
Yeah.
Sometimes it takes a lot of steps, sometimes it does not. Okay, that one took a lot of steps, and I write really big anyways. Questions?
I just don't know how to get it out.
Okay. Woo. Okay. This one does not look pretty. So which side is more complicated, the left or the right? The left-hand side is by far and away much more complicated. If you look at the right-hand side, it's 2 secant x. And normally, don't want to work with secant x, but make a note, what is the secant? The secant is 1 over the cosine, so this is 2 over the cosine. So if I work the other equation to get 2 over cosine, I'm good, because if I were working the right-hand side, that would be my first step to do this. And then how do I get from 2 over the cosine to this nasty thing? That'd be really, really hard to do. Okay, I wouldn't want to try it. So I'm going to start with the left-hand side and make it look like 2 secant x. This 2 cosine x, that's not really part of my work, but it kind of gives me an idea of where I'm going. If I can get to the cosine in the denominator and a 2 in the numerator, I know I've met my goal. I just need to make one more step to get it to look exactly like I started with. That kind of helps me get there a little bit easier. What is that? What do I need to, what's the step before? What's the step before this one? This is going to be the step before that one. Sometimes it helps to think backwards a little bit too. Okay. So on this one, okay, I have 2 fractions. Best thing to do, combine them up into 1. Common denominator, combine them up into 1. So I take the first fraction and multiply it by 1 minus sine x over 1 minus sine x to get 1 minus 2 sine x plus sine squared x over cosine x 1 minus sine x. Common denominator. Notice I did not multiply out my denominator. 90% of the time, leave your denominators in factored form. Do not distribute. 90% of the time, that's what you're going to want to do. And if you think about it, I want cosine in my denominator. That's going to give me a cosine in my denominator. Second fraction, I need to do the same thing, only I'll multiply by cosine x over cosine x. Okay. Which will give me the same denominator, right? Cosine x times 1 over 1 minus sine x. My numerator will be cosine squared x all over cosine x 1 minus sine x. And technically, these are 1 fraction here. 1 minus 2 sine x plus sine squared x plus cosine squared x all over cosine x 1 minus sine x. And all I did, combine them up into 1 fraction. Get a common denominator, combine them up into 1 fraction. Yes.
Is 1 minus 2 sine x, is that what it says?
Yeah.
Okay.
Because when you take 1 minus sine x times 1 minus sine x, FOIL it out. If you had 1 minus x times 1 minus x, what do you have? You'd have 1 minus 2x plus x squared. That's the same thing, only sine x instead of x. Same idea. Okay, somebody have an idea for my next step? I can't cross anything out yet because it's all added and subtracted.
Sine squared.
Yeah. Sine squared plus cosine squared is equal to what?
So that's just one.
1. So this becomes 1. Right? Sine squared plus cosine squared is 1. Combine up like terms. 2 minus 2 sine x all over cosine x, 1 minus. What's 1 plus 1? I love when I get to say stuff like that in a class like this. Come on, what's 1 plus 1? You should know what 1 plus 1 is. I know. Okay, you got an idea where we're going next? No. Common factor. What's my common factor in my numerator?
Oh my.
Factor out the common factor of 2. And I really hope you can see what comes next on this one. The 1 minus sine x is canceled. You get 2 over the cosine of x, which is 2 secant x. That's a horrible 2 secant x2, which is what we wanted to get. Thoroughly frightened?
Yes.
So, here's what I hope is happening for the most part. That occasionally you can see what the next step is going to be before I do it. I do not expect that on every step that we've done so far. A lot of these, I don't necessarily expect you to see the first step on these. But I do expect you to start to see where some of the next steps, what some of the next steps are. The other thing I say is, okay, I know how he did it, and I understand how he did that. Like, how do I factored out the 2? Do you understand factoring out the 2? I had a 2 in both terms. I factored 2 out. What's left when I factored the 2 out? Okay. Ooh, replace sine squared plus cosine squared with 1. Combine them up. Start to see not necessarily the step that I do, but when after I do it, okay, that makes sense. Okay, I see what's happening here. Okay, I know you're going to struggle. It's going to happen. Okay, you're going to struggle with these. That's life. It's what it is. And without struggle, there's no growth. Okay? And some things are going to be harder than others. I am confident that you will be able to do some, if not all, but that's okay. Okay, ready to go on to the last one? Questions? Okay. Suggestions. Suggestions. Anybody? I'm asking for suggestions.
Start on the left and change one side.
Yeah, start on the left and take the cotangent and the tangent, right? And change them to sine and cosine. So I get the sine of theta is equal to, times cosine theta over sine theta plus sine theta over cosine theta Yeah, distribute. Distribute the sine theta. So on the first one, your sines cancel and you end up with the cosine of theta. On the second one, you get sine squared theta over cosine theta.
Could you also do a similar thing with sine parentheses that you did on the previous problem?
Yeah, I can kind of do,
Like you're doing.
yeah, get a common denominator. That would be one of the things to do. It's not the only thing to do, but getting a common denominator, that would be the thing to do. There's actually more than one way to do this particular problem. Okay? I actually have one way of doing it on here, but there is another way of doing this problem. There's more than one way to do this problem. So, get a common denominator. What would my common denominator be? Cosine. So, I don't need to change the second fraction. I only need to change the first one. Cosine theta, multiply it by cosine theta over cosine theta. And I get cosine squared theta over cosine theta plus sine squared theta over cosine theta. Put them together. Cosine squared theta plus sine squared theta over cosine theta. 1 over cosine theta. And that equals the secant theta. Now, so here's what an alternative for this one was. Like I said, there's more than one way. When you get to this step, what you could do instead take sine squared theta, substitute it with 1 minus cosine squared theta. Cosine squared plus 1 minus cosine squared. You combine those up into 1 and you get 1 over the cosine of theta, which is the same thing. More than one way to do the problem. More than one way to do the problem. I think this one is a little bit more visual. I think this one you guys saw faster would have seen this one, seeing this substitution here. Once again, it works, but it's not necessarily something you might have seen, but somebody else might have seen that. Ooh, sine squared, that's 1 minus cosine squared. Maybe that'll help me combine them up. And that one would work as well. So there's more than one way to do a problem. Often with identities, there's more than one way to get to the final answer. Okay, just because one method works doesn't mean another one won't. So don't be afraid to go down a different path. And if you get stuck, like I said, just start the problem again. Try something different at a different step. Try a different substitution. Try a different simplification. Don't be afraid to try something different if you get stuck along the way. What you were doing may be okay. What you may change it over to may also be okay. You just don't know sometimes. Okay, this is going to be a lot of trial and error on today's work. An awful lot of trial and error on today's work. Okay. Questions?